This is a keynote talk at the HAAPIE 2020 workshop in conjunction with the ACM UMAP conference. The topic is on building user trust in recommendations via fairness and explanations. You might have heard of the controversy regarding the Compass software system. It is a risk assessment software that estimates the likelihood of a criminal to commit another crime. It is created by Northpoint and is based on a detailed profiling of criminals. This system is used by judges in the US to help them in their decisions. In such high-stakes environments, the question then is, can we trust such a system? ProPublica, a news organization, set out to investigate how accurate the predictions of Compass actually are. They studied more than 10,000 cases, and they found a bias against blacks. There are almost twice as many false positives involving blacks than whites, and there are many more false negatives involving whites than blacks. With findings like this, it is natural for people to not trust machine-made decisions. A recent survey asked 5,000 consumers how they feel about AI systems. Only one-third said they are comfortable interacting with AI systems, and only 9% felt very comfortable. More than half of the people said that an AI system can be biased, and also believe that it is impossible to design a system that behaves morally. Around the globe, in the past few years, there have been several guidelines published prescribing the ethical principles AI systems should follow. A detailed review of 84 such guidelines identifies 11 key ethical principles. The two most frequent encountered notions are that of transparency and fairness. Transparency is associated with concepts such as explainability, interpretability, and disclosure. Fairness is associated with non-bias, non-discrimination, and diversity. Trust as an ethical principle is encountered less frequently in the guidelines, but this does not mean it's less important. Rather, trust is like the end goal, and the means to achieve it is via the other principles, and particularly fairness and transparency. In the remainder of this talk, I will cover some basic concepts about fairness and explanations, and sketch some future directions about how these two principles could work together to promote user trust in recommendations. Let us first have a closer look at fairness in the context of recommendations. In general, fairness is a highly overloaded term. It can mean different things to different people and can be interpreted differently depending on the context. Let us look at some standard sources for defining fairness. First, we have a dictionary definition that defines fairness as the state of being free from bias or injustice. Well, that's pretty much what everyone agrees fairness means. In political science, we encounter a more nuanced definition. The concept of distributive justice talks about the fair allocation of resources among diverse members of a community. So now we see justice or fairness as an issue of fair allocation of resources. But when exactly is an allocation considered fair? Here we see different possibilities. Fairness can mean equality of outcome, where each person gets the same amount of resources. For example, each person has an equal amount of wealth. But this situation might not be the ideal. Another one could argue that fairness means equality of opportunity, where each person has equal grounds for competing for the resources. Then the amount of resources that end up at each person depends on their individual efforts. No person is disadvantaged at a race for collecting resources. Another viewpoint may equate fairness to social welfare. Going away from individuals, what benefits the society the most is what is fair. So we start to see how fairness can have different but still valid viewpoints. Moving to legal systems, we see the definition of fairness as non-discrimination. Also here we see different concepts of fairness. Disparate treatment is a type of unfairness. It is the intentional, direct discrimination on protected groups, defined on race, color, and gender. In this concept, fairness is equivalent to color blindness, meaning that one should not look at the color of a person to make decisions. An example of disparate treatment is when you force only blacks to take an assessment test before you hire them. Another type of unfairness is disparate impact. This is a rather indirect discrimination where a procedure or decision has a disproportionate impact on protected groups. Continuing this pre-employment assessment test, here you test all applicants. However, based on the results, only blacks are excluded from the hiring process. Interestingly, note that this notion does not care about why disparate impact occurs. It only cares if it occurs or not. Another notion associated with fairness is affirmative action. Here, fairness is when you promote non-discrimination and explicitly support historically disadvantaged groups. A similar notion is that of quota systems. A common example is when you enforce a quota in the hiring process to address the gender imbalance in STEM professions. Let us now focus into how fairness is translated in the context of AI or ML systems. Fairness was first studied in the context of classification tasks, and more recently in ranking and recommendation tasks. Different notions were introduced for classifiers and then transferred into other domains. Naturally, there are quite a few definitions that are seemingly disjoint or incompatible with one another. Even for classification alone, Arvind Narayanan identifies and discusses 21 distinct definitions of fairness. It is quite a challenge to keep track and have a grasp on them all, but I'll guide you through one single definition, easy to remember, and which hopefully rules them all. Fairness is the absence of harmful discrimination. Okay, so I admit this is quite abstract, so let's try and make it more concrete. First, as a side note, we're talking about harmful or unwanted discrimination or bias. And you may wonder if harmless discrimination exists. Well, it does, and you can think about recommenders. They earn their living by discriminating on us. It's just that they call it differently. It's personalization. Perhaps a better term for the type of discrimination or bias that does not lead to harm is differentiation. So let's make this simple definition more concrete by answering some questions. Just to be clear, we are talking about discrimination from an AI system, but by extension, the owner of the system might be responsible. Okay, but why discriminate? There could be various reasons. It could be due to decisions made by the system owner, for example, for business reasons. We might then even question whether the system discriminates intentionally or not. It is also possible that the reason lies in the training data, how one collects them and what they choose to collect. So we refer to the answer to the why question as the sources of discrimination. Note that, as we saw earlier, fairness is not concerned with why something happened. Explanations, on the other hand, are, as we will talk about later. Let us pose more critical questions now. What is discrimination? Well, it's the difference in the treatment or impact of people. That means that we compare individuals or groups of people with each other on how they are treated or impacted by the system. Okay, so what constitutes harm? Here we are not talking about physical or mental harm. According to Kate Crawford, there are two types of harms, although the boundaries are not always very clear. There are representational harms, such as misrepresenting people in terms of their race or gender, or doing some stereotyping. And there are also distributional harms, where some resource is unfairly distributed. We can now focus on recommended systems specifically. I claim that all or almost all fairness concerns that you encounter in the context of recommendations are about distributional harms. So now we can have a single definition of fairness that applies for recommendations. Fairness is the fair distribution of a resource. Okay, so I've still cheated. This is quite abstract, but let's make it more concrete by answering three questions. Fair for whom? When is the distribution considered fair? And distribution of what resource? Fairness for whom? Well, recommended systems are actually multi-sided with different stakeholders. In the context of fairness, Robin Berg identifies two important sides. There are the consumers, the end users, or simply the users, those who receive the recommendations. And there are the providers or the suppliers, owners, producers of items that are being recommended. So harms can be afflicted upon consumers or providers or upon both. For example, in the case of, let's say, dating recommendations. These harms can be financial, ethical, or even with legal repercussions depending on the type of resource being distributed. Another dimension of the for whom question is how do you compare to see if discrimination exists. One way is to consider what is called individual fairness. Here you compare two or more individuals that are similar in terms of demographics, qualifications, or some domain-specific similarity function. For example, individual fairness can capture whether two similarly qualified people receive the same job recommendations. Another way to compare is by studying group fairness. Here you compare different groups of people where the grouping attributes, like demographics, are often called sensitive or protected attributes. For example, group fairness can capture whether blacks receive similar recommendations as whites. One way to remember and discern between individual and group fairness is to think in terms of groups of similar people. If the comparison is within a group, then it's individual fairness. If the comparison is across groups, then it's group fairness. Next question is when the distribution is considered fair. The answer essentially defines when the distributional harm occurs, and it depends on the resource being distributed. Nonetheless, we can distinguish between two main ways to define fair distribution. The simplest is equality, where you require the distribution to be uniform across individuals or groups. The other way is to distribute the resource proportionally to some given target distribution. For example, if you're implementing an affirmative action where you hire with a fixed quota, like one woman for every man. It is often convenient to first define when a distribution is perfectly fair and then measure unfairness by quantifying how far from the perfect fairness state you are. For example, one can say that one wants an equal distribution and then measure deviations in terms of the Gini coefficient or by means of statistical divergence. The most important question to define fairness is to understand what is being distributed. Well, what are the resources that can be distributed by a recommender? There are two main resource types. The first is utility. This captures how relevant or accurate the recommendations are. Note, for this you need to collect feedback to quantify it. The other resource type is exposure. Exposure captures how much the system promotes items to users. And because exposure is not concerned with how relevant recommendations are, it does not require feedback. We will see concrete examples in what follows. First, let us talk about utility. Typically, utility concerns the consumer, so it is measured from that viewpoint. Hence, people often equate consumer fairness with utility fairness, but that is not always the case. From the consumer viewpoint, the most well-known work is from NIPS 2017, where utility is measured in terms of rating prediction accuracy. The fairness goal is to have balanced prediction errors between the protected and the non-protected consumer groups, so that both groups enjoy a similar quality of service from the recommender. But more recently, a provider viewpoint is considered, and utility is measured in terms of ranking accuracy. The fairness goal here is to have balanced ranking accuracy for different provider groups. As in the previous work, both groups should enjoy a similar quality of service. The difference is how you measure quality of service or utility, and that the concern in this case is for providers, whereas in the other case was for consumers. Exposure is typically measured from the items or the provider's viewpoint. Hence, in contrast to utility, provider fairness is often equated with fairness of exposure, although that is not always the case. For example, there is a consumer viewpoint where fairness is defined when recommendations of desired items appear equally frequent to protect and non-protected consumer groups. The idea is that both consumer groups should not be left out of desired items. The resource being distributed here is the number of recommendations or the exposure of desired items. There is, of course, the more common provider viewpoint that says each provider should have equal chance of being promoted to consumers. We can create a taxonomy of fairness concerns or definitions in recommendations by classifying along two dimensions. For whom is the concern, for consumers or providers, and of what is the distribution of accuracy or exposure. Some representative work in this field is then classified along the two dimensions. We observe that most of the work lies into two boxes: accuracy fairness for consumers and exposure fairness for providers. Let us now have a closer look at explainability in the context of recommendations. Just as recommendations appear everywhere, you can notice that explanations often accompany them. For example, in Amazon, you often encounter recommendations which are always accompanied by a short explanation, such as "these items are frequently bought together." Similarly, in Netflix, you have many lists of recommendations, and each one has a short textual description explaining why these items are shown. So why do we see explanations along recommendations? As discussed earlier, the obvious reason is to build user trust. But of course, there are several other purposes for presenting explanations. For example, you may want to promote transparency by explaining how the system works. You may want convince users to buy a product, or you may want to allow users to better express their preferences, or allow the system owner to debug weird recommendations. There is an important distinction between a white box and a black box recommender. An explanation should express how a system works. Of course, this is only possible if you have access to the inner workings of the recommender. For example, if you are the system owner. In this case, the model is available and we talk about a white box model. More often, however, the recommender should be treated as a black box model with no knowledge of its inner workings. In this case, we can only try to interpret how the model behaves. That is why people often talk about explanations for white box models and interpretations for black box models. But here we refer to both as explanations. There are two popular paradigms for explaining black box models. The first is called local proxy models. When faced with a black box, you cannot see inside it, but you can observe its inputs and outputs. Then you can use these observations to explain a given input-output pair, where input in our context means preferences or prior feedback, and output is the recommendations. The key idea is to build a white box model that you can control. The first thing you do to build a local proxy is to slightly perturb the original input and collect the outputs. Then, using these input-output pairs, you fit a white box model, and finally you use that model to generate explanations. Another way to handle black box models is via counterfactual explanations. To understand them, consider a simple causal relationship. If X had not occurred, Y would not have occurred. This essentially explains why Y occurred. The cause is X. So let's see how this idea applies to explanations. A counterfactual explanation of a specific recommendation describes the smallest change to preferences that results in not seeing that recommendation. For example, if I want to understand why item Y was recommended, I need to look for small changes to input preferences so that item Y disappears from the recommendation. These changes are the cause for the recommendation of Y. If the original input, the preferences, is the factual, the changed preferences are the counterfactual. Let's see an example from a recent paper. Alice interacts with a recommender and leaves behind feedback traces. For example, she bought some hiking shoes and reviewed a camera. Based on her perceived preferences, the system recommends a list of 5 items. Alice wonders why she was recommended the backpack. So the system tries to change her feedback so that the backpack is no longer recommended. In the end, the system finds that if Alice had not done 3 specific activities, she would not be recommended the backpack. This is a counterfactual explanation explaining the cause for recommending the backpack. I will close with some ideas for future work on how to combine explainability with fairness. Consider a user, either a consumer or a provider, that wonders whether the system treats them fairly. How can we support such a fairness-oriented request for explanation? If the user is treated fairly, how can we provide an assurance that the system is indeed being fair? In this case, we are talking about an explanation that acts as a fairness assurance. If the user is treated unfairly, how can we explain this unfairness instance? In this case, we want an unfairness explanation, which can be the basis for further investigation. For example, the user may then wonder if this unfairness violation can be justified somehow or could have been avoided. In both cases, we talk about fairness-aware explanations. The paradigm of counterfactual explanations seems to fit nicely when we want to convey facts about fairness. But fairness-aware explanations are different from conventional explanations in two main ways. First, the desired output that we want to explain is not unique. In conventional explanations, we want to see when a particular recommendation list appears. In fairness-aware recommendations, we want to see when the output is more fair, and this can happen in different ways. There is not a single output that we are targeting. Second, there may be multiple input-output pairs to explain. In conventional explanations, there is always a single input-output instance that requires explanation. However, most fairness definitions are based on aggregating multiple instances. In this case, it's not clear how to look for counterfactuals for all of the instances. As a conclusion, I want to leave a simple takeaway message. To build user trust in recommendations, we need to invest in techniques for explainability and for fairness for all sides at stake. There are interesting research directions to explore individually at fairness and explainability, but also at their intersection. Thank you very much for your attention.